And so this is the PV phase diagram, sort of a classic one. And we've looked at this in the previous set of notes, but let's just refresh ourselves. This one has solid-liquid equilibrium. So let's walk on an isotherm. So I'm at a particular temperature, and I'm compressing the gas, and the pressure's going up, and then I hit this point right here. What happens? Condensation happens, and so a droplet of that substance starts to form. And then as long as there's liquid and vapor in equilibrium, the pressure is constant. That's the vapor pressure of that substance at that temperature. So we're following a particular temperature. So right here, we have the water droplet here at this PV, and we have the gas at this PV, and in between we just have the lever rule. So if we happen to be at this volume, we have a balance between the number of moles in the gas phase and the number of moles in the solid or the liquid phase. And we would determine how many moles are in each using the lever rule. When I talk about the lever rule, let's see, we've got folks from a lot of different places in this classroom. Have y'all ever seen this piece of playground equipment? A seesaw, yeah. Is this, you know what I'm talking about? Okay, so if the seesaw is not if it's poorly constructed and one end is longer than the other, how are you going to get it to sit level? That's right. Okay, and a little bitty kid over here. All right, and so this is the number of moles, and then this is the length, L1, okay, is equal to number of moles and L2. That's the lever rule. And so we can determine how many moles are in each phase if we know where the volume is. The volume is the fulcrum, and we can measure the difference between the volume of the liquid at that temperature and the volume of the gas at that temperature and the volume of the piston. Okay. Now how would I know the volume of the gas at that temperature or the volume of the liquid? That would be the volume of that number of moles of gas and that volume of that number of moles of liquid. Okay. So we need to know the total number of moles before we can decide how many of those moles are in the gas and how many of those moles are in the liquid. Okay, and so that'd be another classic problem to do, would be the lever rule, and you put the fulcrum someplace in between and solve for the number of moles in each phase. Okay, we could do this in N1 L1 equals N2 L2. Okay. And then N total is equal to N1 plus N2. Did y'all have seesaws when you were little? Yeah. Yes. We had one at the baseball park, and it was really pretty cool. Yeah, but you had to trust the other person. Did they ever jump off the seesaw? You get you at the top and jump off, boom, And so the ballpark had 3 seesaws, and someone said, "Hey, you want a seesaw?" And you say, "No offs." And they say, "No offs." That was our thing. You had to promise, kind of like a pinky promise. No offs, no offs. Okay, then you can seesaw with that person. If you had a friend you could really trust, you could stand on the seesaw, and they would put you up in the air and hold you there because there was a mulberry tree. And you could pull the mulberries off and eat them. And so if you really trusted them, they'd hold you up and you'd get some mulberries and eat them and save some for them, and then you'd give them to them. So that was a great memory. I was probably 5 or 6. Yeah, I can still remember doing that. It was great times. So let's continue on our isotherm. So now we've pull the volume all the way to the liquid volume, and there's no more gas left, and the isotherm goes like this. Now in the previous phase diagrams, we didn't have the liquid solid. But at this point, you've pushed on it so much and you've compressed the liquid that it starts to solidify. And so you start to get some crystals or some amorphous regions, but anyway, a solid phase starts to grow inside that liquid. And so we have another lever rule problem right here between the solid and the liquid. As we compress it, the liquid is being compressed a little more and it's pushing it into the solid phase. And eventually now we're pushing on the solid. And the solid has got a compressibility too, which may be steeper than the liquid. But that isotherm goes up very steeply. So there, the compressibility of the solid. We're pressing only on the solid. So you should be able to walk through this phase diagram in all of these different directions. Follow an isotherm. So let's label those. This is an isotherm. Wow. That was bad. Isotherm. What is this green line here? Iso pressure, yes. But yeah, isobar. Yeah, that's right. And if you look at a weather map, the contours that you see on a weather map are isobars. So they're looking at high and low pressure in the atmosphere, and wind goes from high pressure to low pressure because there are no walls up there to keep the so this fluctuations in pressure are how we track our cold fronts and our warm stable areas.
I still have to ask a question.
Yes.
I'm still not 100% clear on how it works. Will you, from the critical point, will you draw and shade the supercritical fluid
Yes.
area?
Okay. And then let's finish this last label, this red line. What is that one? And then we'll get to your question. ISO, because it's same something, same what? Same volume. I think there's an E.
I don't think so.
No? Isochore, isocore, I don't know.
I think it's just core. If I remember correctly.
Yeah, so anyway, I have to Google that. Someone Google that on their phone. Okay. So that's the isocore, isobar, isotherm. Now there is an isotherm that goes through the critical point, and that would be TC. So the critical temperature goes right through this critical point. There is an E, okay. Oh, stop. Okay. So hard to be accurate with this pen. It's better than the mouse. So that's the TC, the critical temperature isotherm, okay? And so you've got to be above that TC for a supercritical fluid. You've got to be above that also in terms of pressure. This would be the supercritical pressure. So this is PC. And in order to get that high pressure, you really need to be smaller volume than VC. So those are your boundaries. You've got to be in this shaded region above that. So this is the supercritical fluid region. Make sense?
So to the right of that, it's still a gas.
It's a less dense fluid, and eventually it becomes what we would call a gas. But there's no phase boundary. We would draw a line there if there was a phase boundary.
Right.
But there's no phase boundary. So it doesn't go from a fluid to a gas and go, wow, I crossed this phase boundary. There's no phase transition between supercritical fluid and gas. It just becomes less and less dense. But I would say if you go past the VC here, even though there's no line there, if you go past this, you're out of the supercritical fluid region. Help? Okay.
I needed something kind of.
Yeah, that's as concrete as I can make it. So if you want a supercritical fluid, you need to be below VC for that number of moles. Now it's going to be dependent upon the number of moles.
So would there almost be a supercritical fluid gas? You have a solid liquid line and,
Yeah.
and a liquid gas line. Would there also be like a supercritical fluid line, gas line?
No, that's what I'm saying. If there were, we'd draw it. Yeah.
Fuzzy.
Yeah, it's just a smooth transition from gas to supercritical fluid when you're above TC. When you're right at TC, then you see that supercritical point, and there's some crazy things that happen there.
Most textbooks will just have the two colors kind of like show. Like,
Yeah, they'll just blend colors. Like if they have a supercritical fluid color, then it'll just kind of fade to the other color. Yeah. Right. So that's the PV phase diagram. Ask your questions now because we're about to change to PT. Okay.
I like PT more, so good.
Yeah, and this is on the video, so the little lines that I've traced and everything, you can go back and review it. I want to be able to ask you, if I drop you anywhere on that diagram, you can tell me where you are and what your properties are. Okay? If you walk along any one of those lines, like let's walk along A, we start in a solid at one atmosphere pressure, we're on the solid, we start to, it probably makes more sense to compress, but we could pull a piston on, pull a vacuum on that solid, but we can't change the pressure, so we just increase the volume and then that solid can melt. And then we have the liquid, and then we start to form some gas, and then we have all gas.
Would you give it to us labeled like that, or do we need to remember solid?
Like if I draw, no, like take off all the labels.
All?
Yeah, take off all the labels and you see this. Can you tell me what's in all the different regions?
You can mention this through.
Yes.
Say the pressure.
Is arrow A and arrow B both isobars?
Yes. Yeah, both A and B are isobars, and B is below the region where you'll have any liquid at all. So you can't have any liquid at B. And so you have sublimation. So down here, this is solid going straight to gas. So here's the solid, here's the gas. So if you would calculate those 2 points based on the number of moles. And so that would be, the far left would be the volume of the solid, number of moles of solid that you have. If it's all solid, and over the far right, that would be the volume of all gas of that number of moles. So it'd be a lot larger, right? Like 1,000 times larger. And then if your volume is anywhere in between there, you're in equilibrium between solid and gas. So you have this sublimation happening. And that's what happens at 1 atmosphere for CO2. So solid, dry ice, we call it this subliming. So at room temperature, and at least in 1 atmosphere, we don't have the ability to have liquid CO2. We'd have to raise the pressure quite a bit to get up into where we'd have liquid gas equilibrium for CO2. Question?
What's your way of simulating volume changes in your head? Because pressure is kind of easy to think about, and temperatures is
Yeah, the good question. He says, how do I think about changing volumes? I think of a piston chamber. So I think of a chamber that has a movable wall. So mentally, whenever I'm thinking about volume, I think of a variable volume like this, where I can move that wall in the chamber.
It's hard to discern that from pressure, though.
Yeah, and so what could possibly keep the pressure the same if I'm opening the piston up, right?
Raising the temperature.
Yes. So this is not necessarily an isotherm. Okay. This is. I mean, yeah. I guess. Let me change that. When you're in these middle regions, it is an isotherm. Okay, because you have equilibrium between solid and gas down in the line B. You have the equilibrium between solid and gas. So that is the vapor pressure, although it sounds weird, vapor pressure above the solid. Well, I guess we would call it the sublimation pressure.
So it'd be whatever temperature keeps that pressure the same for that
Yeah, yeah, yeah. But then when we get over here in the all solid, that line across there, we couldn't keep the pressure the same and expand the volume without adding temperature. Okay, because we would have cooling upon expansion. Okay, and the same with the gas. We couldn't have an isobar in the gas phase without adding in temperature.
So why is it triple line and not triple point at that very, very small peak right there?
Okay, so in this, you see it's a line.
Yeah.
So the triple line in this phase diagram has got 3 phases. It's got solid phase, liquid phase,
That's right, yeah, right there.
and gas phase.
Right.
Only on that line do you have all 3 phases in equilibrium.
But I guess that the middle point is where I was like, that probably is where the triple point is.
No, this is in this phase diagram. There's no triple point. Okay. We'll see in the next phase diagram the triple point.
Yeah.
But in this one, it's a line, and so you need that line so that you can do your seesaw. Only now we have 2 kids on the seesaw. 3, I mean. So if our fulcrum, our volume is here, then we've got a tiny kid here and 2 medium-sized kids. Okay, holding the thing level. And so that's going to be a tricky lever rule to solve because you have, 2 equations and 3 unknowns. The 2 equations are the total moles equals the 3 individual moles, and then you've got 3 lines. So now we have a triple point. So this is the PT phase diagram. You're probably more familiar with this one. Okay. Let me go back one more thing though. If I take all the labels off, what do you start with? I'm going to leave the axes labeled, okay? So you know at least it's a PV or a PT, okay? So you see a PV diagram, you got these regions on there. Where do you start? You know, like if you're attacking an island, you need a beach head to land. You're not going to land where there's a cliff. So where's your landing point?
Or gas.
I hear some people say gas. What are you saying? You're saying that way. So that would be the gas. Yeah. You said solid? Yeah. So we have different things. And conceptually, that's fine. That's your landing point. But if you think about low pressure, big volumes, gas. That's sort of mine. Okay. But you could also do small volume, high pressure, solid. Okay, yeah, so either one of those I think is a safe place to start. So you can start up here and know, okay, I know this is going to be a solid. If I've got all of these equilibrium areas, I know this is the solid. Way out here, big volume, low pressure, that's a gas. And so down here, that's got to be between solid and gas. And then this has got to be between solid and liquid. Liquid only exists in this small region here. And then that's going to be liquid and gas equilibrium in that. Make sense? Yes.
I'm not exactly sure with line C. I know it's mesochord, but what is exactly happening?
Okay, so if we start at a particular volume, so we're in a container that's of a fixed volume and we're really low pressure and low temperature, we've got a solid vapor equilibrium. So that solid has some vapor above it. And again, these are in equilibrium, so it may have to sit for a long time for that solid to come to equilibrium with its vapor. Okay, and so we have a fixed volume, and so the only way to really raise the pressure is to raise the temperature. Okay, but we raise that temperature a little bit, and the pressure adjusts. And so we've adjusted how much vapor pressure and how much solid we have. Now, if the vapor pressure goes up, the solid's going to decrease in its amount because we've got more in the vapor phase, and so the solid moves over here to the right a little bit. The vapor moves over, gets closer to the fulcrum, so that means it gets more abundant. Then we get to this point, we have some liquid starting to form. So we've raised the temperature. Some of the solid is melting. We still have vapor pressure, but at that triple line, we have solid, a little bit of liquid, and some vapor. We go above that temperature, then the solid is completely melted. And now we just have vapor and liquid in equilibrium. And we keep raising that temperature, the pressure keeps going up. And so we're just going from isotherm to isotherm. We're not on a particular temperature, we're raising the temperature. And since we have a fixed volume, the pressure is going up too. And our phases are adjusting as we go up. Now, when we get to this point here, okay, then we will sit there until all of the liquid is boiled away. Okay, and so then when all the liquid is gone, we're just heating the vapor, and the pressure is going up and up and up.
So is that a teeter-totter also? Going from the triple line to the liquid
Since-
gas line?
No, the only teeter-totter is the horizontal lines. So when, like, we're right here, we don't have any vertical teeter-totters. Is that what you're asking? Yeah. So we're just moving the temperature up, and we just always have this balance in the number of phases. So think about this as we're heating this liquid up. Look at what line's getting closer and closer to our isocore. So this is the fixed volume. So that's where our little fulcrum is. That's the balance point of the teeter-totter. Okay? And which kid's getting fatter as we go up?
Both equally.
The one on the short end of the stick. And it makes sense. As we're raising the temperature, the gas phase is growing in number of moles. And the liquid phase is shrinking in the number of moles. And so then eventually the liquid phase goes completely away as the kid is sitting right in the middle of the seesaw, right here. And so the other kid has disappeared. And now it's just all gas.
But that would be almost like the seesaw. I mean, you said that there's no vertical seesaws, but if we put the seesaw point on there, going from the solid gas, from the triple line up is liquid gas, so we have two components.
The triple line's not liquid.
Well, I'm saying not at the triple line, but above the triple line.
There's no line there. So you have to, wherever you are in volume, you have to draw a horizontal line to the next two lines.
But you just said that as the kid's getting fatter as you're moving up.
Yes?
So
We're at equilibrium. So if I go from this temperature here to that temperature here and let equilibrium establish, some of this liquid will evaporate and it become over here. And so this, this is still, this length has gotten a little bit shorter, but that one's gotten a lot shorter. And so the number of moles of gas compared to the number of moles of liquid has really grown. So at every new temperature, we draw a new line and we do that ratio, that balancing point.
For that one.
I understand that, but
Yeah.
I'm saying because.
But I don't think there's anything to be gained with the vertical teeter-totter analysis because there's really nothing at that triple line. I mean,
I'm not saying
yeah.
add the triple line, but I'm saying that you're only dealing with liquid and gas,
Mm-hmm.
and so the measurement, the ratio above, like so where you drew the dot on the line C,
Yes.
the amount above it is shorter than the amount below it.
I don't think there's anything to be gained by that. Just that you're closer to totally evaporating the liquid. Yeah.
Okay.
Yeah. Yeah, I don't think there's nothing physical about that except that you would be closer to totally evaporating the liquid. Yeah. Yes. Okay. Now here's a PT phase diagram. Someone check the time for me. Here we go. How much? 3. Okay. So once again, looking at all of these properties, here we have pressure in atmosphere, temperature in Kelvin. One atmosphere is labeled, and so that's going to define your normal melting and your normal boiling point. So this would be melting point and boiling point at 1 atmosphere. So those are your normal melting and boiling points.
This is not water.
Right. Yes. And so if we're here, we've got a solid, we're heating it up. At this point we stop until all of the solid has melted and become a liquid. So we can sit at that temperature until it's all melted, and then we move forward and we're heating up the liquid. Here it starts to boil. Okay, we're at a lower pressure, so we must be in Denver or someplace like that, up in the mountains. We have a lower pressure, and so it boils at a lower temperature. Okay, so you got to cook your noodles a little bit longer, you know, because it's not as hot and it doesn't get into the starchy stuff as easily. Okay, here's that triple point where you have all three phases in equilibrium, and here's the critical point above which you have the supercritical fluid. So in this region, I would draw a line there as the critical pressure, critical temperature. So this would be the region for the supercritical fluid. So it has to be a higher temperature and a higher pressure for the supercritical fluid. Down here at B, we have the sublimation. And so all solid, subliming at this line here, and then all gas. And then here you're just following, you're letting the pressure change with temperature. So that's probably following that isochore, and eventually you leave. So the one that we had before, the C, that's the line for C. And here we've left all of the liquid behind, and we're just warming up the gas.
So those two are linked.
So let me go back and look at C. See, we have C there. So I've drawn this line C on this diagram right there. Yeah. Okay. And so I'll put on here for this one CPV diagram. And we can stop there.